This is a new topic, preliminary calculus. So this is the calculus we look at in year 11, okay? So mainly what we do, we use calculus to find the gradients at particular points on a graph, whether the graph be a straight line or a curve. So far we know how to find the gradient of a straight line, but we don't know how to find the gradient at a particular point on a curve. So what we do know how to do, for example, if I've got a straight line, we know that the gradient of this straight line, you know, is rise over run. So you'd go rise over run. Some people do the run first, then the rise, okay? And we've seen that before, y2 minus y1 over x2 minus x1. That can also be written as delta y, which is the change in y. So that is not a triangle symbol. That means the change in y. So this symbol is change in y. So it's really the change in y divided by the change in x values, okay? So the gradient of a straight line is the same, so anywhere along that line, the gradient's the same. If I did the gradient over here, or if I did the gradient there, the gradient would be the same on any part of the straight line. Okay, so the gradient of a straight line is the same between any 2 points on the line, it's constant. And also, you know, we've seen this before, we've got positive gradient, zero gradient, negative gradient, and undefined. The reason this one is undefined because gradient is rise over run. And there's all rise, there's lots of rise here, but there's no run. If I pick 2 points, yeah, I can rise, but I can't run. And when you divide, when you divide something by 0, that's when it's undefined, okay? The reason this gradient is 0, again, it's rise over run. There is no rise if you're picking 2 points on the line, but there is run. So you are allowed to do 0 divided by a number to get 0. Okay, so we've got, now you already know all this, positive, zero gradient, negative gradient, undefined. Now, just looking here, let's say we have this graph here and a computer is depreciating in value, just getting you to work out the gradient just from what you know. So you can pick any 2 points on the graph, it doesn't matter. I might go from there to there. It's obviously a negative. It says by how much does the computer depreciate each year? Just have a look at your graph. How much? 500. And now calculate the gradient of the graph. What do you think the gradient of the graph is going to be? Without even thinking. Anyone? Oh, let's do it. Gradient is rise over run. Now, any 2 points, I'm going to rise, say, 1,000 from there to there and run backwards 2. Can you see that? Or I can do you want me to do rise over run or y2 minus y1 over x2 minus x1? It doesn't matter. All right, so if I'm doing I would have, this is the 0.1 1500 if I did do it that way. This is the 0.3 500. If I wanted to do y2 minus y1 over x2 minus x1 over, it's 1 minus 3, I would get 1,000 over negative 2, which is negative 500. Now, why do you think the gradient is negative? Well, it's because it's like that. But see how the computer goes down in value by $500 each year, which is why there is a negative gradient. So the gradient represents the value that the computer depreciates by each year. This is the distance a car travels over time. That's the distance with the time. Calculate the speed. How do you work out speed? Well, let's see how far it goes in 1 hour, ladies. How far does it travel in 1 hour? Anyone? 60. Well, speed is 60 kilometres per hour. That's just by looking at how far it travels in 1 hour. Also, you might say, well, I know that distance is speed times time, so speed is distance over time. This is another way you could do it, so that at any particular point, the distance here is 60 kilometres and the time here is 1 hour. So it's 60 kilometres over 1 hour, which is 60 kilometres per hour. I could have also chosen this point and done 120 kilometres divided by 2 hours and get 60 kilometres per hour. But you can just see how far it travels in an hour. And the gradient, we know gradient is rise over run. I'm just going to go from there to there. So what's the rise and what's the run? Rise, run. What is it? 60 over 1, which is 60. So the gradient represents the speed or the rate of change of distance with respect to time. So speed is how the distance changes with time. The gradient is the same as the speed. In the other example, the gradient was the same as the rate of depreciation. So therefore, we can say that gradient measures rate of change. All right, speed is a rate of change. It shows the rate that one quantity changes with respect to another. Okay, now, all good? Let's look at this. Now, gradient of a curve. That's what we're really looking at. So straight lines is fine. We know how to do that, but we need to look at gradients of curves. So could we use the formula gradient is rise over run, or y2 minus y1 over x2 minus x1 to calculate the gradient at a particular point? You can't. No. Because, for example, if I want to find the gradient of the curve between these 2 points, I know it's pretty much, I know it looks like it's straight on the line, but a curve and a straight line are not the same thing. I can only find gradients of straight lines, and this, even though it's fairly straight there, it's still a bit of a curve in that section. Like if I want to find the gradient from, say, there to there, that's a straight line, the other bit's curved, so you can't, okay? It's because, because y2 minus y1 over x2 minus x1 measures gradients of straight lines only. So it measures the gradients of straight lines only. So it's just saying now mark on the curve where the gradient is positive or negative. So tell me here, tell me about the gradient. Negative? Good. So I'm just going to do this in another colour. So I've got gradient is negative, negative. Would you say negative? What about down here? What's the gradient down there? 0. What about this gradient? Positive, 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 all positive. What about here? See, when you want the gradient of the curve, you look at the tangent to the curve. So up here, the gradient here is 0 because it's like the tangent to the curve. Tell me about this gradient. So this is gradient 0, negative gradient, 0 gradient, positive gradient, 0 gradient. What about this gradient? Negative. Okay. So it says mark on the curve where the gradient is positive or negative, which we've done. Positive, positive, okay. Where is the gradient 0? We've marked that. Draw a straight line with 0 gradient through these points. So here, gradient 0 at that point, and it's 0 at that point, okay. Okay, so those lines that I've just drawn in pink, they're called tangents to the curve, okay. So this is where the gradient is 0 there and the gradient is 0 here. Here we've got negative gradient, positive gradient, negative gradient. And also, if you're going from positive to negative numbers, you have to pass through 0. See, negative gradient, 0, positive gradient. All right, later we're going to learn and look at gradient just as numbers, all right? And that 0 is between positive and negative numbers. Right, the tangent to a curve. So a tangent, you've already seen in circle geometry, tangent to a circle. So this is similar. A tangent is a straight line that passes through point P on a curve such that the tangent has the same direction or gradient as the curve at that point. Therefore, the gradient at tangent P and the gradient of the curve at P are equal. So what we do, we work out the gradient of the tangent at that point, and that's the same as the gradient of the curve at that point. So here, if we look at point P on this curve, that's the gradient of the tangent. Well, the gradient of the curve would be whatever the gradient of that tangent is. Here as well, at that point, the gradient of the curve is the same as the gradient of the tangent. Here at this point, if we do a tangent to the curve, that's the gradient of the tangent equals the gradient of the curve. Same for these. Oh, what's the gradient here of this one? What's the gradient? I can see it. It's flat, 0. And here. Now, what we need to look at here, yes, this is the gradient of the curve. Gradient of the tangent at P equals gradient of the curve at P, but the P has coordinates A, comma, and I'm just going to write function of A. You know, when we use function notation. So you know how P is the points X, Y? I can see that P has X value A here, and its Y value will be whatever I substitute. When I substitute the X value into the equation, or into the function of X, that's its Y value, function of A. So it says, consider two cars. Car A drives along the curve, and car B is parked on the tangent. All right, so when car A reaches the point of tangent C, it will be facing exactly the same direction as car B. So let's say car B is here, right? Car A is here, and it drives along to reach car B. When it reaches car B, they're facing the same direction on that curve, if that's a road or something. Okay, so therefore both cars will have the same gradient at X equals A. So again, the gradient of the tangent at P equals the gradient of the curve at P. Again, a tangent, as we said, how do we find the gradient of a tangent to a curve? A tangent is a straight line, so all we need is 2 points on the tangent so that we can use our gradient formula for a straight line, right? However, the problem is that we only know 1 point on the tangent at P, right? So how are we going to do this? Now, remember, the coordinates of P are found by substituting the X value of P into the equation of the curve. All right, which is function of X. Again, if this is Y equals function of X, the coordinates of P are X, comma, function of X. Okay, X, function of X. Now, problem is we need a second point on the tangent. So the only points we can be sure of are the points on the curve, Y equals function of X, because we have its equation. So this is what we do. When you want to find the gradient of the tangent, you just pick the point at P and another point, this is just for introduction, very close to P. And the closer this Q gets to P, gradient of that, the closer the gradient of PQ gets to the gradient of the tangent. All right? So at the moment, this gradient's fairly different to the tangent, but if I bring Q in closer and closer and closer, this is where limits come in. We're going to be looking at the limit as Q approaches P, or as that the distance PQ approaches 0. We're going to be doing limits, all right? So what we do, instead of, you can't put 2 points on the tangent, so we put 2 points on the curve. 1 point is at the tangent, and the other one is at a second point close to P, and it's point Q. So we can calculate the gradient of that. We're not actually going to be doing it yet, all right? And we know that the gradient of PQ is close to the gradient of the tangent. Now PQ, just like in circle geometry, is called a secant. So PQ is called a secant. Now, however, so the gradient of this line is not equal to the gradient of the tangent, but it will be close. But however, as Q gets closer to P, the gradient of the secant will approach the gradient of the tangent. They'll get closer and closer. Look, if Q's up here, the gradient's like that. Q comes in, it's closer. It's almost getting to the same gradient as that line as Q gets closer to P. So we'll use this idea to find the gradient of the tangent. So remember, PQ is called a secant. Okay, now let's calculate the gradient of the secant PQ. You can just do that by Q has coordinates. What are the coordinates of Q? 1, 2. All right, let's do the gradient of the secant. Isn't it y2 minus y1? Over x2 minus x1. So what's that? 5 minus 2. Is that right? Over 2 minus 1. What's that? 3. Gradient of the secant is 3. Let's work out the gradient of the tangent using rise over run. All right. Can you see 2 nice points? There's a nice point. I can see the point 1, 1 and the point 2, 5. Can you see it? How much are you rising? How much are you running? What is it? Girls, what is the gradient of the tangent? I've got 2 points. Anyone? The tangent is at P. Isn't it 4 over 1, which is 4? Girls, can we see that? The gradient of the tangent's 4. The gradient of the secant at the moment is 3. But if I keep moving point Q closer and closer to point P, I will eventually approach a gradient of 4. I know the gradient of this tangent is definitely 4, right? But as I move Q a bit closer and closer, my answer will get closer to 4. So if you consider moving Q along the curve towards P, so when Q is very close to P, comment on the gradient of the secant compared to the gradient of the tangent. So what do you think? So as Q approaches P, I'm just going to put that the gradient of the secant gets closer to 4, which is the gradient of the tangent. Now I could, what I'm going to do, look, I'm going to do this all using GeoGebra in a minute. We don't have to do these calculations. They're all going to be computer done on the computer. All right. So look, I'm not going to do a calculation there on the curve because we're doing it with using GeoGebra in a few minutes. So therefore, as Q reaches P, what do you think happens? The gradient, come on, of the secant will equal the gradient of the tangent. So as Q reaches P, the gradient of the secant will equal the gradient of the tangent. So now we're going to demonstrate this in some GeoGebra files. Okay, we're now going to GeoGebra.